That's true. I wish I had one.
Know anything about issue 7?
Talking about Ohio issue
Yeah,
7.
yeah, it's this clean energy thing, but like, I couldn't find much on it. The itself was really vague, and I couldn't find anybody that was source other than the condition, so, you know,
Yeah, I don't know. I honestly, I don't. Is it on the ballot?
yes, yeah.
I should know. I voted that today.
Chilling after.
Didn't actually say
It's like
anything
there's
about
that
using
paper
clean
that
energy
was
at
gonna
all.
talk to me
I
about,
think it's just moving
but
on.
like,
Yeah, so it
my
is,
like,
it's
because
good,
I'm
it's
in the
good.
final, and I'm just final.
But it had like all these buzzwords, making
This
it
one,
like,
I
oh,
haven't tried it.
on its face, it seems like this could be, you know, a good thing, but I don't know deeper. Another single source I could find was for it.
Yes.
That's funny. Interesting. I'm sorry. I wonder if it's a response to the whole household thing, you know. Either,
And the rest is like.
reestablishing RBS or higher levels. I don't know, but I had not.
When
I didn't think
that
there was
way,
gonna
it's like
be
it is
any
what it is. I appreciate it a lot more, just like, you should learn. Yeah, I learned more and I feel less stressed about it. But last night and today were yeah, and Friday. Right.
It was like.
All right. And at this point, I'm like, I'm gonna admit something, it's like, it's stuff that I don't know, like, what is this even mean? And analysis to get into of the data collection. Like, it's like, we're the message they use.
Yeah.
Like, good practice.
Oh, yeah. I was
Like, they don't talk about the methods. So, yeah. I'm just gonna say, and that's like one that has like an out of 5. So it's like more so, but I might just like. My exams, and I got like Arizona. Kelly, are you good? I have a midterm this week after our. What is your time? Yeah. Have you had one in that class yet? Or was it in person or online? It was online. It's like one of their some of the questions I was like, yeah. Like that's like some of the graphs. I really like our professor. Alan Flavor, funny guy. I was like, I didn't know there's two in my class. Yeah. I know, I love it all. But it was like, we had to just Chelsea specifically, Chelsea doesn't get. Everything learned in that class. That's not true, because everything in 4330, the second one, is builds off of what you learn in that one. So I like, actually, you remember more than I thought. But, like next semester is gonna be fun, because like, I've been taking like theory, yeah, I grab my iPad. I literally meant to charge it for a big class game, and I forgot, so now it's at like 6%. Most of the time. And motivated to do something.
And that's my point, is it just pretty soon?
Very welcome.
That's fine. I'm sure that
So Bruce, I thought you said your wife threw that out. Jack, you messed up my story. I'm gonna tell my story about this.
Get out of the car, just get out of the.
I should have.
So the question for everybody here. For 8 minutes with the team last week. Everybody, did anybody not do that? Did not want to make it? That's good that you did it then. I was gonna do your demonstration last week. So. Remember, it's the 19th, right? 19th is the date that the written things due. Have past time to be able to do that. We really want you to do it. We know you will. Every one of the passes are really good. I can't think of one of them. But one of the presentations or written things are all really good.
Yeah.
So beautiful pass. So yeah, keep up. I mean, keep up the. We got a challenge for that, guys. Pass. But you know, you guys speak a lot more than pass. Yeah, something else. Yes.
That's right. We got a guest speaker. Yeah, Chuck is still coming on Thursday. Yeah, Chuck Seville is actually someone who was my first hire when I moved to AEP. And now he's the president of all the unregulated businesses at AEP. So he's done very well. And he gives a really good presentation. So really interesting. He talks a lot about renewable energy and a lot of the thrust in the electricity business, but also a lot of the challenges of that. But in this presentation, you'll see I actually probably repeat some of the slides that I stole from his presentation previous years. So,
That's a pretty good presentation. I mean, it's worth coming to that one, folks. I mean, you know, you can watch it online. I might even, we might even offer a little extra credit for coming on Thursday. It's worth showing up for it because
yeah,
there's someone who actually knows. Not the first cousin.
yeah, he's in the role of it. Really working on a lot of those issues. So. Yeah, the other thing to mention, Brent, I don't know, did you mention in class about the sustainable energy
Well, I
class?
mentioned it once before, but probably let's mention it again.
Yeah, I just people be aware that we've got kind of it's structured as an independent study, so it'll be a pretty small class, which is fine. That's kind of the intent. First year for sustainable energy. We'll obviously focus on sustainable energy economics. You know, sign up for it. And, it'll get into a lot of things that this class just kind of touches the surface. So we're gonna, when I talk today about renewables, I'm really gonna focus on wind and solar because those are the two fastest growing renewables right now. But there's sizable amount of renewable energy from hydro, biomass, potentially geothermal, other things that we'll get into more in the course. And we'll get into some other clean energy sources that have some issues like nuclear. So, yeah,
What's the course number?
it's
4190.
4190. Yeah. And I have to, there's some glitch. It says needs instructor approval. I had someone who was trying to sign up said they couldn't sign up because of that.
But that's really easy to accomplish. Except that we talk to the advisor and except,
Right. That's right.
I mean, I'm listed on the course too, but Bruce is teaching. I don't know why they put it on there.
Yeah. That's fun.
Was that? Yeah, 4193. We can find a phone number out of that. Pre-grade class. What's the time?
It's from 12, 12:20 or 12:30 to 2:10. Does that sound right? I think that's right.
Probably at 12:45.
12:45 to, yeah, like 2:05. That's right. So afternoon class, don't have to get up early for it. And the other thing, just is how it's going to be structured. We'll have a midterm, but there won't be any final in it. Final is going to be projects, or we'll have an individual project to develop kind of a report, presentation around a specific prompt related to one or other technologies or approaches or energy efficiency or something like that. Kind of choices the students. Depends on how many students I have. If we can have a lot of students, more than we expect, then we'll make them through the project. We probably don't need individual project. So should be interesting. Okay, so let's start with speaking of renewable energy. Let's embark on this. We could, by the way, we could put the flyer on Carmen. I'll make sure we do that so you guys can see some of the specifics. So today it's renewable energy. So first of all, wanted a green jacket, right? Green for renewable energy. This jacket actually has a long history, as you can tell. Comes from literally about 40 plus years old jacket. Green jacket's pretty well, it's in good shape for 40 years old. Of course, I haven't worn it for about, other than like one day a year, some of these classes, I seldom wear it anymore, it's out of style. Brent remembers that actually when I teach the energy trading class, we talk about different goods and what trades, and you need volume, and you need something that's homogeneous. And I said, well, this is kind of the polar opposite. This is something that you couldn't trade. You wouldn't have a market for it. You wouldn't have a futures market for it, et cetera. So, okay, so let's start off on renewable energy. Some nice pictures of wind, very, very small local solar there. And so we're going to just kind of go through some background on renewable energy, some history, some forecasts, big forecasts that you'll be seeing, as you've seen in some of the other parts of this course, is what EIA is projecting in their annual energy outlook going forward. And like many, they're projecting a very large growth in renewable energy, renewable capacity, particularly for solar and wind. And we'll talk a little bit about some of the policies that have been in place historically and the impact that they have, as well as some of the economics. And the electricity economics and the cost of electricity, which have all gone through, renewables fits in that pretty well, but we do have one item that's different, which is something called the production tax credit that makes it a big difference for a lot of the renewable projects, certainly historically, and even some going forward until that credit expires, or depending on what's in the final I guess clean energy bill, for lack of a better term, this fall that ultimately passes, you could see that being extended further. Okay, so what is renewable energy? The sort of classic dictionary definition, people being replaced by natural ecological cycles or sound management practices. And so that's a pretty broad net as to what that would mean. It's not just wind and solar. Wind and solar are the most obvious, the first ones people do think of. Obviously, hydro is a big one, particularly if it's on a river hydro. It's considered more renewable, if you will, than if you dam up a stream. And once you've done that, obviously, you change the ecosystem. And that can't necessarily be replaced by natural ecological cycles. So it's low head hydro is one thing. Dam hydro is quite another. You got wood and biomass. They're renewable, right? You grow wood or grow crops, grow trees, and you use the biomass. And from a CO2 emissions perspective, it's net neutral, right? Take in the carbon in the atmosphere to grow those plants, and then you turn around and burn those plants and produce energy. And net, you're at zero. The geothermal, that's a real interesting renewable source. Some parts of the world, Iceland jumps to mind since their country is almost 100% renewables. Quite, but they're very, very close. And a lot of it is from geothermal. Because effectively, the country's built on volcanic rock. There's a lot of hot gases just below the surface, so you can use geothermal processes, use the steam and convert that to electricity. So that's kind of a nice one because what's the supply? That's effectively infinite, right? There's an awful lot of part of the crust of the earth, heat and molten rock, and that's going to stay basically indefinite as long as the earth is around. But the thing is, I've just described these, and there's some others we can think of. There's tidal power, there's other sorts of sources and different types of biomass, just the conventional, anaerobic, gesters, and algae, biomass from algae, which is another form of renewable energy. But the regulatory or policy definition is often somewhat different, right? So in some requirements, renewable portfolio standards we'll talk about later on, wind and solar would count, maybe no hydro would count, or maybe all hydro. So it varies. Sometimes biomass and wood count, sometimes they don't. Geothermal counts. So just keep in mind that when people use the term renewable energy, it's laden with different meanings depending on who you're talking to, whether you're talking about policy, regulatory definition, or whether you're talking about a ecological definition, etc. Yes.
I would just add on that, right now there's a huge debate and discussion about wood as whether it's renewable energy and whether it's carbon neutral in fact.
Yeah.
And in fact, because there's enormous amounts. So Great Britain, this is relevant right now because Great Britain, there's a problem with wind power there. There is a problem, continuing problem with wind power. It's producing below level because they haven't had enough wind. And they have the world's largest wood-fired biomass power plant.
Yep.
And they're importing all of the wood for that from the US actually, from the southern US. So it's become a really interesting sort of issues that, there's lots of people who like that not to be considered because of concerns about how timber harvesting affects forests in the US or elsewhere. And then there's the fact of it, which is that as long as trees are growing, it actually is carbon neutral. Right. So it's just, there's an interesting debate discussion, very high level science debate. That really, I guess it's Great Britain and Denmark and yes, the Netherlands, the three big, Sweden, and Norway, I guess, are
Right.
two other countries use a lot of wood-based biomass energy. And it's-
Yeah, I mean, you could, with biomass, and boy, that's a really good point, because there were some definitions, as they were kind of struggling with the regulatory policy definition in this area, where they would say, oh, well, it is renewable, it does count, as long as you can point to a specific crop you're using, basically using, fueling and then replanting it, right? Kind of a closed cycle. Problem with that, of course, we all know, so particularly within this course, is that nothing really is truly closed. And you can look at this and say, well, okay, they're doing that, but did that somehow influence how much planting of trees is going on elsewhere? Less so.
change the prices.
So it changes the pricing, it has all sorts of effects, so it's not as obvious how to deal with it. Wind and solar are pretty clean. You can look at those and say, all right, I produce a wind plant, that's electricity that comes from a renewable source. No real difference. Likewise, solar. But some of these others that you get out, and geothermal certainly, but some of these others you get into some of these issues.
Just mention geothermal as well. There's a fellow over in civil engineering, Jeff Leck, they said interacted with him. He's a pretty well known expert on geothermal. It's super interesting.
Yeah.
I mean, just the ability to, it's really interesting, just these dynamics of water flow underground, understanding that, and the heat exchange with that. It's just, there's a lot of technology that's, that can be exploited, but it's complicated.
Yeah,
That's what limits it in a sense, like the technology is so complicated.
Yeah, the technology is complicated. The one big plus with geothermal is that there's one thing that a lot of engineers have worked a lot on. It's drilling holes in the ground.
Yeah.
Now, there's been a lot of that in the US, and there's a lot of experience with it, and they've gotten better and better at it, right? We talked about natural gas, horizontal drilling, 3D seismic, fracking kind of technologies. Those are all, developed over time.
With
Same
the
thing
exception
with
of
geothermal.
entrepreneurship campus, when they couldn't accomplish it, those of you, none of you were here a few years ago, was trying to do this. I mean, they spent an entire year and a half going up south, Camp South, over whatever that thing is, over there, that grass up there across from Hyde. I mean, it was great, they were doing geothermal there, I was working these things, put in geothermal over there. They thought they could drill, and spend an entire year and a half drilling.
Yeah.
Never worked out for them, though.
So the other thing that is often touted is somewhat of a myth, right? Renewable energy is always environmentally friendly. Well, it's not always environmentally friendly. There are some trade-offs. In fact, almost any source of renewable energy, you've got some issues, some trade-offs that are worried about. Wind, you've got the migratory birds, and bat deaths and stuff, and they do a lot of planning to try and avoid that. They have to, as part of environmental impact statements and things like that, they have to do for these bigger projects. But it's not, you're basically got these giant windmills out there, and they are going to affect birds and bats and other flying critters. Biomass and wood, you've got local air pollution, right? Anyone who is and bigger scale biomass wood power plants have pollution controls on them, but pollution control equipment. But if any of you have ever experienced, as many of you had, walk through a neighborhood in the winter, and all the fireplaces are going full bore these days now. They've got their, wood burning, fire pit outside. We got a lot of air pollution. That's one of the biggest sources of kind of particulate and NOx and other things out in the atmosphere. So it's not without its problems. Hydro, we mentioned. Central station solar, big issue there is a huge, we'll show a picture of one of these coming up. It's a huge land footprint for solar, just enormous, for a sort of equivalent amount of power. You know, one of the sort of contrasting it to something that's kind of almost the opposite. One of the advantages that nuclear has over solar, not that I'm trying to tout nuclear, I kind of look at them all with pluses and minuses. Nuclear is very energy dense. You know, other than the fact that they need some space for the containment buildings and more concrete, things like that, which doesn't use up more space. But you can produce a heck of a lot of power in a relatively small amount of acreage from a nuclear plant, which would, you know, be thousands of times much land for solar. So that's an issue. Another big issue with solar is, of course, we've got the rare earth metals issue. These days with, you know, lithium being big for batteries, and certainly you have lithium and cadmium that are used in kind of the solar collectors. You know, guess where most all of that is being produced these days? It's in China. So it's not only an issue of rare earth metals and mining, it's also an issue of maybe being able to get it at some point. So that's a concern. The other one is renewable builds mean zero carbon emissions. So one of the problems with that is that if you put in intermittent renewables like wind and solar, and you don't have battery backup, and today you really don't have economic batteries, starting to change. You're seeing a lot more going on, a lot of it going on in California. Seeing some grid batteries have started to make a difference around the country. But nonetheless, when we put in those renewables, the problem is the sun goes down, or more probably of a bigger issue is when the wind stops blowing, you don't have any power. So you need something to back it up. Typically, that's a fossil source. Typically, that's these days natural gas. It could be coal, et cetera. Obviously, those have carbon. So you have to be careful when you say, all right, well, this will reduce so much. Well, yeah, but then it means you're using this to replace a fossil source. You're still going to need some of that fossil source in effect to produce the electricity over the course of the day. And here's a graph. This was actually taken from a study back in, when I first started showing this graph, it was only a couple of years old, and now it's about 7, 8 years old. It was like 2013 or 2014. And this was looking over a time period. This was actually plants in Europe where they were looking at normalized generation. MIT was looking at this. And you can see this is just a group, it's actually a group of plants, it's not just one plant. But you can see the levels of generation and how much they fluctuate over time. Now, one thing is the solar follows a definite pattern, right? You see less in some days, there's a rainy day, right? Not much. But generally it's lots of power in the middle of the day, a lot less after that. But wind, like almost no rhyme or reason. I mean, it's up, it's down, it's up, it's down. So this is a big issue. And that's why battery power is so important. Or it might actually be, you know, other types of batteries, not just at the power plant itself, but actually in the grid. So that you're in effect backing up power from that area with batteries. But batteries are pretty expensive.
How expensive do they usually go?
What's that?
How expensive do they usually go for?
Well, it's hard to, you know what, it's hard to measure. We're used to thinking of things in dollars per kilowatt of capital costs. And in that measure, it's, you know, on the order of, I think, $2,000 or $3,000 a kilowatt. It's been coming down. But what's more significant is how much energy does that end up storing? So it's really in kilowatt hours. A little tough, but generally it's quite, I guess the way to look at it is it's quite a bit more expensive than the alternative if it were fossil. And, you know, one so far with renewables, one of the, you know, this is showing, I think this is ERCOT, this is Texas. Chuck is going to probably show the same chart. So you don't understand it this time, you have another chance, Chuck. And what this is showing is that the output versus the load. You see the green is the output for, down, let's see it. Yeah, I think the wind output is in green. Yeah, that makes sense. And the load curve, the peak load, electricity, which is a daily cycle, follows that pattern pretty much every day. And here's the problem, right? It's August 30th, 2018. The peak load was about 68,000 megawatts. The wind resource was only about 2,000. So, you know, on average, the wind might be, you know, around 10,000, 8,000, right? But if the wind happens to drop off, it's one of the things with wind is hot summer day down in Texas, and the wind just quits, right? And that's when the load really goes up. You got to crank the air conditioning up. It feels miserable out there. It's humid. Air is still. And then you have this. Now, Texas is somewhat unusual so far because it is the leading producer of wind. And so wind actually is part of its grid, depending on the time of year, et cetera, can make up a fairly large percentage of electricity used. Most states, including Ohio, it's pretty small now. So right now, if you put a wind plant in Ohio or a number of other places around the country, you wouldn't have to worry about the intermittency too much because there's a lot of other resources that are being load. But as wind and renewables continue to grow, and they're growing very fast, this issue becomes more and more of an issue. And we know, of course, it's interesting that this chart was ERCOT, and then you all heard what happened literally this past winter, where ERCOT had all sorts of problems. Blackouts and outages for weeks, you know, kind of a combination of a somewhat freak snowstorm for Texas. Some snow in Houston, which never happens, but very cold temperatures too. And it just led to a cascading set of problems. The wind was down, what solar they had was down, but they also had a lot of freeze up of gas lines, and so gas plants couldn't turn on, and it just went on and on and on. And that's where you just don't wish you had a lot of that. Yeah.
You think that ERCOT is, Texas is willing and or able to connect themselves more with other energy grids that doesn't happen?
I'm sure they are looking into that, but one of the things that is unfortunately a function of history is that you've got three major grids in the US, and typically to move power between those grids is, other than, let's say, a few thousand megawatts, but moving tens of thousands of megawatts is very difficult. And I think it's more technical. Then you get beyond my understanding of the physics, but it's pretty complicated, but it has to do with the synchronous nature of the grids, and they operate at different cycles, et cetera. And so you can move powers in between them, but you have to do some somewhat special things. And they do have connections between ERCOT and what's called the Eastern Interconnection. And I think also with the Western Interconnection. It's the other way. It's a good question because it's an obvious sort of solution. Boy, if we could have gotten power from, Missouri, Oklahoma, some other places, even East Texas and Louisiana, et cetera, they might have been in better shape to provide, have some excess capacity.
It is fascinating that a state that fancies itself a free market state and we, to some extent, being part of an even freer market. Because they could, presumably, they could fix the challenge, they would have to change the engineering of it, I guess, the frequency, whatever, right? I mean, I guess that is a big thing, it's like costly to do that. I guess that's part of the time, it just surprises me that they would want to be part of the market.
I don't, yes, I'm not, I don't think they have an issue with being part of a free market. I think it's, as you say, it would be surprising if they were in that spot because they've been one of the early ones to go to full deregulation and they have a market. But they do have some things in their market and in sort of how utilities and plants sort of prepare because there are some logical things that should have happened. For example, there should have been sort of ability to have backup fuel at, say, a gas plant. So that as a freeze up, it can just turn on and use distillate oil instead during that period. And a lot of plants didn't have that. That was big. But you're right. I mean, being able to integrate with other grids more, obviously helpful in the situation. Thing is, except for this kind of emergency, there isn't much transfer that goes on normally. I mean, it doesn't even get to the limit typically of what runs because there's resources. There's a lot of resources on a normal day in Texas. It's just, this is crazy. We have. All right, so this is kind of renewable energy. This is kind of the history of the US, right? Starting in 1776, it's all wood. Everything was wood. Then all of a sudden we got coal in the last half of the 1800s, became more dominant. We even saw the first of other renewables, which was hydro. See down here, this swath, it gets pretty big, particularly in the middle 1900s. You had the New Deal under FDR, where a lot of the major dams in the United States still exist. Grand Coulee Dam, a number of others were built. And so you saw a big increase in hydro then. And then, of course, the nuclear era here. But again, the real renewables, these are all green in the sense that they're non-fossil, right? That's the way they define it here on the EIA chart. But look, when you look at wind and biofuels, all other, I think it's probably mostly solar in this graph, you can see what a small percentage it is. So if you blew this up, as we will in a second, you'll see that it's growing very rapidly, particularly in the last 10 to 15, maybe even 20 years. And here's a look at renewable energy consumption. Now, this is across all sectors. So like this chart, right, we're looking at all energy consumption. We're not just looking at electric. We're looking at vehicles, transportation, industrial fuel use, residential, commercial heating, which is direct use of fossil fuel ordinarily. And you can see that sort of dominant share. When you get bore down on the renewables, truth is, well, it doesn't get a lot of fanfare. Biomass is the biggest. Why? Well, a lot of industrial use. Think of pulp and paper companies and how they probably handle heating their power plants. heating their facilities. The biomass is pretty high when you look at it across the whole economy. Biofuels, yes. Yep. That's the other thing. Transportation of biofuels. But electricity is more of a real growth story, right? Renewable electricity has really grown. Now this is historically, again, renewables in this definition pretty much includes anything other than nuclear that's non-fossil. So it counts biomass for electricity, it also counts obviously solar, wind, geothermal, which is only a small amount in the US. But it also counts hydro, and really all hydro. So hydro is most of this, and some biomass for power. And then in this growth, really, you see almost an inflection point, 2010. And that's where we've seen the big growth in wind, and now increasingly just the last few years it's solar. A lot of electricity production from those. This is a EIA 2021 case where they said, all right, well, what about varying renewable costs? So we don't know what they're going to be. We've got our estimates, but some people think they're going to go down further. Some people think that they're not going to go down further. In fact, they're going up over time. And you can see what difference that has in terms of the projections. Here, the projection is just straight up for renewables. Here, it's kind of flattens out more. And of course, their reference case is sort of in the middle. But the interesting thing about that is it shows how sensitive it can be to weather. And then we can kind of see that when we do our cost of electricity calculation. So if the wind plants cost $1,000 a kilowatt, that's pretty darn good. If it costs $2,000 a kilowatt, that's not so good. Likewise for solar, etc. And here's the wind and solar sort of domination. And if we look at via selected fuels, again, you can see this is in their reference case. It kind of got natural gas, it's increased to 40%. And over time, again, these are percentages, not absolute totals, but over time, the percentage from natural gas is going to drop in the reference case, while the percentage of renewables is 42% by 2050. Now remember, these are projections based on whatever the current policies are. This is not assuming that what's it called? Build Better. Build Back Better. All Build Back Better passes in terms of green energy or not. It doesn't include, maybe one might project the US, and they're very serious about getting to carbon neutrality, that they'd have actual legislation that would push that down. That doesn't seem to be in the cards right now, but that could be part of the trend. But they're just saying, oh, this is kind of the business as usual world now, based on the economics and cost trends that we see. So even with that, you still see a pretty strong growth in renewable energy. And well, where is it coming from? Well, here's the interesting part. We'll show it in some of the other graphics, get into more of the details of that. But look what's going to happen. First, historically with wind, which is this green area here, right? That's grown a lot. You see this sliver of solar, and then all of a sudden, solar really takes off. And this is the utility scale solar, right? That is really driving that. And some of the economics, which has improved a lot, as well as the fact that solar really has a better possibility to use batteries to augment it, right? think of it this way. The natural pattern with solar is energy during the day, kind of peaking in the late afternoon, then starting to drop off as the sun sets, eventually down to zero. Well, if you knew that, you kind of design batteries that store some of that power and then use it for those evening hours where you still have high loads in a lot of areas. That's not such a hard problem nor as costly as dealing with wind, where you say, well, when do I store this? Because I don't really know when it's going to stop being windy. Now, maybe you can use good forecasting and stuff, but even then, a little more difficult to sort of store energy for something that might happen in a few days as opposed to every day. So I think that's another factor. I will, EIA does not say that explicitly, but I'm saying is that that's probably one reason utility scale solar is going to be a big growing area versus, let's say, wind. Yeah.
What do you mean utility scale solar?
You're going to get to it. I'm going to show you what I mean exactly. Here's just a series of additions of capacity. And we can see that kind of the dividing point of 2020 here, where it's historic. And then once you get beyond sort of 2025, these are really EIA's own projections. These are the actual next 2 years and the ones that are pulled in the pipeline, right? These are wind plants are being constructed now or being planned now. There's solar plants likewise. And that's kind of there. And then you get into this 2025 and later, and that's really more of a EIA projection of how much more is going to get built. Again, you can see lots of wind early on, but mostly solar longer term. Is that realistic? Maybe. Again, a lot of factors go into that, a lot of assumptions go into which one dominates. Yeah.
So you're talking about like batteries for solar, and I know that's like one of the big issues. And do you think that it would make more sense to potentially just, I mean, obviously there would be a lot of like challenges involved at the individual level, but do you think it would make more sense to have like individual consumers of electricity have batteries for their homes instead of having like a massive battery factory that stores the electricity and then keeps it out to the grid? Because I know that like, I think like Tesla sells that, it's super expensive, but they sell a battery that they claim could like run your house for like 24 hours. So would it be like a smarter way to go about it?
Yeah, I think that there are probably two different things there, right? For your home, maybe the reason you want a battery, I know the reason we might want a battery in our house is that we don't want to have an outage hit us and have, our food getting spoiled in the refrigerator, or our sump pump turning off and it's a rainy day and we all of a sudden have a flooded basement, that type of thing, right?
Mm-hmm.
So that's more of a battery for the distribution grid issues. I don't think you would, for the purpose of having relatively cheaper energy because you're using some battery storage to backstop solar, that's more of a, kind of a grid, broader grid battery type issue.
Yeah.
If that makes sense.
Mm-hmm.
Yeah.
Thank you.
Well, we look at wind, and we'll kind of delve into wind here, and I'm going to, of course, move along as usual. This is a map. It's kind of hard to see it, but you can certainly see it when you look through the slides. This is the scale of wind power density, truly wind speeds. When you think of it, the darker the area, into the gray, the black areas, those are the areas that have the most concentrated wind. Kind of average wind speeds, maybe the way to think of it. Okay. So what's very striking in this map is when it comes to at least places that are relatively close to some major population centers, a lot of it is down here. And then, of course, you see you got some along the Appalachians, right? The wind tends to, and of course the Rocky Mountains some out west as you get into the Sierras, right? Wind tends to have greatest differentials, so therefore wind speeds and weather occur often around mountain ranges, right? That's pretty common. And so what it turns out is if you look at this overall, that West Texas, this area near the Panhandle, is very heavily promising for wind technology. That's one of the reasons Texas developed it so much. But even in Oklahoma and moving up to all the way up to Nebraska, and the Dakotas, all this area has a lot of wind. Ohio, it's okay, but it's not as great, right? Except around the lakes, right? Around bodies of water, so around oceans and lakes. That's where you get into the possibility of offshore wind. Obviously, coastal wind is probably the best, a lot cheaper than putting a wind plant offshore. Got to have issues of getting the electricity from that spot all the way from the water cables and things like that. Yeah.
How far offshore could you put us? Could you go, like, I know it's deep. Could you put it?
I think you go pretty far. I know that the North Sea wind, for example, they go pretty significantly beyond. They don't go hundreds of miles, but they certainly go 50 miles offshore.
I know like one big part of that is people don't really want that, like constructing their view of everything. They hold them on my back birthday, so
Yes.
you just like throw them out there.
Yes.
Should that be possible?
There was a wind plant that, to my knowledge, is still not that built, but back, I don't know, 10, Brent probably remembers, it's like 10, 15 years ago, there was a project called Cape Wind. Yeah. It was off of Cape Cod. And the Kennedy family really didn't like it. They had their views from Diana Sport, those areas on Cape Cod. It would have meant that there were these kind of visual impairments. That's an issue, of course. But, in the grand scheme of things, I don't know. I guess if I was lucky enough to have a place on the ocean and I was just looking at towers in the distance, I wouldn't bother me that, right? I'd be real happy to go on the beach, frankly, but yeah, it is brought up, and Cape Wind had this and other, it wasn't just the Kennedy, there was a bunch of people, and they kept trying to get the project done. And to my knowledge, I don't think they got it done. They might have got it done.
I was just looking at Google Maps, I couldn't help myself. England has a lot of these offshore wind farms.
Right.
We can find a few of them. They're not that far. You can actually see some of the wind towers.
Yeah.
It's kind of cool. They're not that far offshore.
Yeah, obviously, there's a big disadvantage. The further you go offshore, the more expensive, right?
It's because you have to lay the cables. I guess they're just hard to, you got to build it. You got to take all the boat has to get all the stuff out there.
Yep. It's a lot, and construction of, electrical transmission, which is a lot simpler. That's relatively expensive. Imagine what it's like putting in underwater cables. Probably underground. All right. So anyway, what this gives you a sense of is the middle of the country is the area where there's a lot of wind has been developed, certainly some out west, some of the western states, and in the, kind of northeast, you can see some of the best spots. Here's a picture of a wind farm. This is a relatively new, meaning it's probably 5-year-old plant. And one of the things, of course, that's really striking is look at that house and then look at the towers behind it and you get a sense of how big these are. And that's, yeah.
Well, actually, but I was gonna say, like, that's like a pretty big house. Those are like really loud. You ever been around those?
Yeah, they are. They make a lot of noise and mostly they are, it's more of a whirring kind of humming sound, I guess would be the way to describe it. But it's still makes noise, yeah. I mean, because it's a generator and it's spinning basically. It's spinning, well, the generator's inside the tower itself, but. And here's to the point of these towers getting bigger and bigger. An interesting graph. This goes all the way out through 2018, and I don't think they've gotten much taller than this. This is half as tall as that. It's about 400 feet tall. That last one, some of the Siemens GE turbines in 2018. And you know, originally I remember working on some of the initial things that AP was involved with. And they were some of these. Everyone was real excited. We've got wind turbines that are, you know, up to 1 megawatt in size. So it's right here. And then all of a sudden, we got to 1.5. Oh my God, we hit the limit. And then Siemens came along back to 2.3. All right, this is all economies of scale, right? The more power you can produce, the cheaper per kilowatt hour these projects are going to be. Certainly the dollar per kilowatt rated of wind then tends to go down, all else being equal. And here's sort of the trend. This is from 2014 to 19. And what you see is that, first of all, they divided it up in this chart. It was an EIA chart. And they divided it up into larger facilities greater than 200 megawatts. Think of that as, you know, maybe 100 wind towers together in a wind farm or more. 100 to 200 megawatts and 1 to 200 megawatts. What they found is the newer ones, as they came online, the average cost per kilowatt was falling for these, but obviously these are already lower. And they got down to 1252 in 2019. So big decline in those costs. Not as rapid as if we'd run this chart back another 10 years the other way. You know, wind towers were costing well over $2,500, $3,000. A lot more expensive. So big improvements. What was that? Again, size mattered, made it cheaper per kilowatt, economies of scale. Also materials, a lot of advances in materials. Now the trick with wind towers is you need the towers to be structurally sound so you don't have an accident. Sure hate to see an accident with a wind turbine. It's never happened, but they design them so that they will be okay and then have very high winds, right? But the other side of the coin is you want to design them so the materials are light enough that it will spin the turbine even at relatively low wind speeds. So that's kind of the engineering, and it got better at doing that. And they created more of these composite materials in the last couple of decades, as opposed to just using steel or aluminum, kind of more basic metals. So between 2011 and 2020, wind capacity, and you can see they are led by Texas, has just about tripled from on the order of 30, I think it was 35, 40 gigawatts, all the way up to 118 gigawatts, and that's in 2020. So lots of growth. That's the big grower historically of renewables. And again, you can see Texas, the Midwest, and the central regions are sort of the leaders, and the Northwest. And the lowest is the Southwest. Some of that's not because the wind doesn't blow in the Southwest, because the alternative in the Southwest is solar. And solar, as we'll see in a second, is very, very economic in southwestern US, meaning Arizona, Nevada, those areas, for obvious reasons. And speaking of solar, here is one type of solar project. This is concentrating solar project or CSP, Crescent Dunes project at 110 megawatts of generating capacity. And you can see again how big the acreage is for that. A lot of acres for 110 megawatts. All right. Interestingly enough, this project is fairly close to another concentrating solar project, which you can see when you fly, if you fly from Phoenix to Las Vegas. Of course, none of you ever going to Las Vegas, I'm sure. Yeah, right. Without the green, you got to wear the green jacket. Lucky green jacket, right? It's really apparent if you're sitting on you're going north and you sit on the left side of the aircraft. I had experienced this probably about 7-8 years ago, and I went, "What is that light?" And it literally looked like a beacon, and that was the concentrating solar. Pretty neat to see kind of that type of project. Now, these concentrating solar projects are not the norm anymore. They were using mirrors as opposed to actual solar panels. Now the norm is this, the photovoltaic central station. And again, in the cars, see how far that goes that way. You don't even know how far it goes down this way. Lots and lots of acreage again. This is, willing to guess this is in either southern Nevada or Arizona, given the lack of houses or anything around it. And there is, yeah, plenty of sunshine. And here's a chart that shows exactly that. These are as of 2019. These are where the facilities are located. And the capacity, which the biggest circles are 585 megawatts. So those are very large solar farms. And you can see California, Arizona, Southern Nevada, heavy concentration, all in the desert areas of the state. And this is literally a solar map. There's I think Google has it. I don't remember who does it, but there's actually a solar radiance map that you can get. You can look at and see where is the most sunshine, most concentrated sunshine. But we all know intuitively where it is, right? It's all this part of the Southwest. And where is the development been? Well, of course, it's where the sun shines. And also because there's a lot more population, somewhat because of some of the portfolio standards we're going to talk about in a second. There's a lot of concentration along the South Atlantic as well. Those are the two big areas. This is an interesting graphic. EIA did this recently. This kind of shows between 2014 and 2017 what the average capacity factors are, right? Remember we talked about how important that is to the economics. And the important thing is some of these areas are getting close to a 30% capacity factor. Doesn't sound great until you realize, well, of course, by definition, the absolute best you could do would be a 50% capacity factor, right? Half the day on average, right? 12 hours of sunlight. And what this is saying is some of these areas can get quite a large capacity factor by a lot of techniques. But again, further south, right? They're southern, more sun year round, and also obviously in sunnier places. And that in turn is influenced where a lot of this capacity is going. Now, we've seen that, as I mentioned, the utility scale, and again, what am I referring to with utility scale solar? Some of these projects we've seen, they're actual, projects that are producing hundreds of megawatts of power, are put into the grid, if you will, to serve power needs across a broad region. Now, we've got also rooftop solar, residential, commercial level. But that's a smaller part of the total piece of solar. It was more visible maybe 10 years ago, as if we talked about solar, most people said, oh yeah, that's rooftop solar. That's a business putting solar panels on the factory roofs, or it's customers, individual customers putting it on their houses. As you can imagine, it just doesn't have the same economies of scale. And that's the big reason that these have taken off. They're fundamentally cheaper, particularly as you can see over the last 5 years. And again, in those areas of the country we mentioned that are got the best solar resources. And here's also what has driven that, and that is average construction costs. And these are for solar systems, again, utility scale systems. And you've had technologies on the silicon side of fixed tilt. Yeah.
Oh, right. I was just gonna ask in the last slide, how come 2016 was so much higher than the rest?
It was a year of expiration of the production tax credit. And so, an investment tax credit. And way Congress has dealt with the production investment tax credit for literally decades is they'll have it, but they can never fit it into the budget unless they say it's for 3 years, the next 3 years, and then it expires. It goes to nothing. And so everybody and their brother says, if I'm building a solar plant as it's coming close to expiration, it's not clear they'll re-up it. They say, well, let's make sure to get our plant in place or start construction in that year so we get the tax credit. Right. So you get this big surge, and then they pass it, and then it drops off the next year. So you can see here, what's interesting is axis-based tracking, right? That's a little more sophisticated, but that allows the panels basically to move with the sun, right? So it's going to produce more electricity, and as a result, the dollar per kW is a lot better at that. That's what we tell it is. What's interesting here is I've never quite understood. This is a much smaller part of the picture. I think this has to do with some of the actual projects, and it wasn't a lot of specific projects for it, but for some reason the axis-based tracking is higher than the fixed tilt with Caddy, and I'm not quite sure of that. But again, this is still the dominant technologies on the silicon side. Okay, so let's talk about policy in the last 15 minutes here. Renewable policy, a big part of it historically in the wind side has been the production tax credit. And what that does is it allows, as of sources, and this is expiring at the end of this year, but if you put in place, if you start construction, get your license, whatever, there's a certain set of things you have to do to quote start construction, then you get eligible for this production tax credit of 1.8 cents a kilowatt hour. And historically, the production tax credit has actually been higher in some previous years, up to as high as 2.5 cents a kilowatt hour. All right, what does that do? Well, it means, think of it this way, that as you run that plant, maybe your total levelized dollar per kW costs are say, $40 a megawatt hour, something like that, 4 cents a kilowatt hour. And this says, okay, you can, for those years, every kilowatt hour you produce, you get a credit of minus 1.8 cents, which literally cuts your cost. And so the total cost at that point by 40, 50%. Huge deal. Really encouraged a lot of wind back, particularly when wind was struggling to be as economic as grid power from, let's say, fossil sources. Made a big difference. It literally was during that period when the capacity quadrupled, where a lot of the production tax credits were ramped up. This is some of the other renewable technologies. The production tax credit has expired, but when you get to the tax credits, you also have the investment tax credit. That's the 30% of capital costs for solar. And if it commenced construction by the end of next year, it's still 26%, but now you can see it's phasing down. Right, so that's another one of those things that would expect you would lead you to believe that there's, particularly as you get right around here, a lot of people are going to start to let's get that plan in service, or let's get it quote commence construction. Again, has kind of a legal definition rather than a physical definition. And then after 2024, and after it goes to 10%. Residential, so again, we're talking about rooftop solar, actually drops to 0 after 2024. And so the ITC is kind of what the production tax credit is to the wind industry. It's had some of the same impacts in terms of costs, and pretty significantly reduced overall costs. Because again, you know, wind is, as you've done the calculations, you know, it's probably 90% capital costs. That's the big cost for a wind plant. It's very little variable cost. There's a little bit of fixed O&M and maintenance every year, but that's pretty much it. Okay, so production tax credit, investment tax credit are very important. Another thing that has driven renewable development generally has been the clean energy or renewable energy standards. A lot of people refer to it as RES or CES. And you can see in this chart that most states have a standard, but they're varying degrees. I mean, some like California, this was done and already they upped that, but they had 60% renewables by 2030 and 100% by 2045. Right? That's all renewables, right? All clean energy, all renewables. New York has a lot. Ohio, a lot less, but it does have a standard. And it's been, because of some of the legislation in the last couple of years, it got capped this 8.5% level. So there's no push to bring it up anymore. And then you've got other states, some are 12, some are, here's only 1.5%, 50, that's 15%, 25% in Illinois, Kansas 20, 15, et cetera. Now, the important thing about these are they're all somewhat different, right? So there's always a tendency to look at the renewable standards and say, oh, okay, this means after California, New York has the toughest renewable standards in the country. They're going to have the most renewable energy. Except that when you start looking at this, and actually I didn't put the other slide, so let me tell you, you'll find that they're all somewhat different in terms of what is counted. So in New York, which uses today, I don't know, about 25% of their energy is from hydro, close to that, maybe 20%. They count all that as renewable, Other states don't count hydro, they only count wellhead hydro. Now, some states will count as renewable using biomass co-firing. You take a fossil plant and use biomass for 10% of the load, and that contributes towards your renewable target. Other states don't. So, be careful when you start looking at these numbers. There's a lot more that goes underneath them in terms of how aggressive the renewable standard is. Okay, other financial incentives. Some states, California being a big one, and remember California has very high state tax rates, and they have a state ITC. So a lot of the burden of state taxes on developing sources, utility scale sources, are offset by an ITC in California. Most states don't have that, but a few do. Some use something called feed-in tariffs, and that's mostly for solar. And that's a way to drive in pricing for solar based on costs. Controversial, right? Rather than having the solar be built and then plugged into the grid, and the market kind of decides what the price is. These feed-in tariffs say, all right, well, the price has to be X for this portion of the generation in order to allow it to be viable. So there's some, pluses and minuses. That's kind of a forced form of renewables in terms of rates. They require the ratepayers to pay for it. And surprisingly, that's not always popular. Right? Net metering is sort of an interesting thing. And really what net metering refers to is residential or commercial rooftop solar are a form of distributed generation. And so that might be, small scale on-site power, such as solar panels at homes or businesses, right? Probably the most prominent example. There are others, but that's one most prominent. If you have a net metering state, typically it allows any excess power that you produce. Let's say your solar panels are going in the middle of the day or business or whatever. You've got more energy or electricity that you're producing than you're actually consuming. So the way net metering works with advanced metering technology is that you're literally selling power back to the grid. Okay, so here's an interesting question. What should the price that you get be if you sell power back to the grid? Well, people who are advocates of net metering and people who are advocates of solar, rooftop solar in particular, would say, well, it's the full rate that I pay for electricity. It's everything. 10 cents a kilowatt hour or $100 a kilowatt hour. Look at it. Maybe on average, some places are higher, 15 cents a kilowatt hour. In California and places in New York, significantly higher rates. The problem with that, of course, is electric utilities in those states will argue, particularly those that are responsible for the distribution end of the system, is, well, that doesn't really cover our costs. So if everyone, let's take an extreme, if everyone net metered, right? Let's say we've got 50% of the population of Ohio all of a sudden put rooftop solar on, there's all this excess power coming to the grid. And they said, oh, you can get a rebate equal to, let's say, roughly that 10-cent rate. Well, all of a sudden, you've got a system that relies on transmission and distribution and retails, and metering and customer service, and all these other things. And that net metering tariff means a lot of that is not getting paid. So, not surprisingly, utilities have said, oh, wait a second, net metering, and here's the opposite extreme, net metering should be fine, but you get the generation rate. You get what it costs to produce the power, but you don't get all these extra fixed costs in effect in your net metering tariff. So those are the two sides of the debate that's going on in a number of states. And not surprisingly, in a few states, it's kind of come out in the middle. Right? So you still get a pretty generous net metering tariff, but it's not the full rate. But it's not just the generation piece. It's kind of where it's ended up. So that's really where you get into some of these states that kind of started to change. Obviously, it's a big issue in states like California, where you have a lot of renewables, right? Again, in Ohio, is it a huge issue? No, because we're like at 6%. And when you actually look at the the rooftop commercial or residential, which is really the only thing that gets real affected by net meter, right? Utility scale solar doesn't get affected by net meter because it's all part of the grid already, right? But that portion is only, maybe 1 or 2% in the state. So it's still not a big deal here, but in somewhere like California, it's become a much bigger deal. The one to keep an eye on. All right, the last thing I'll show you, since we've got almost perfect 5 minutes, is doing the levelized cost calculation. Just take a look at this. I'm not going to go through it with you. The only big difference in all the calculations on the levelized cost of electricity is this last line here, or second to last line, production tax credit. Right? And how was it what I said? It was $40 a megawatt. Production tax is 1.8 cents a kilowatt hour, or $18 a megawatt hour. That means instead of the cost being $40 a megawatt hour, it's only 22. That's huge. That makes it economic everywhere. And not only does it make it economic to displace a new plant, you don't build a new fossil plant, you build a wind plant. In some cases, it displaces. In effect, it says, well, I'm willing to build this wind plant, if I'm going to have a series of sources that I'm looking at. Maybe I'm a large generator and I provide wind and solar and all these things as well as fossil. I might say, well, not only am I willing to do this and build this over other sources, I'm willing to build it simply even if it's not needed, because I know the electricity cost of this all in is greater, or excuse me, is less than the cost of electricity from, say, a gas plant on the margin, which today is maybe closer to $30 a megawatt. So that's a big deal. So the future, right? We're going to see some continued growth, even without the PTC and ITC, and that's not nobody means guaranteed right now whether we'll have PTC and ITC continue, for another 5 years, another 3 years, maybe it'll continue for another 10 years. But it'll still be driven. The state RPSs do have an impact, certainly in states like California and New York. More CO2 regulations, of course. I want to say buy back better. But anyway, okay. If Biden's initiative goes through Congress, that will make a difference. We will see technology and cost improvements happening. Not as rapid as we have seen at the beginning of the growth of wind and of solar, but certainly continuing. A key issue, of course, is the development of a viable economic storage option. And again, don't forget about other renewables, which could play an important role. Again, if we come through on geothermal and get to the point where, doing all the fine science of figuring out hydrology and everything else, and we get better and better at doing that all of a sudden geothermal becomes very interesting. Because you know, the nice part about geothermal, its capacity factors it effectively almost 100%. Remember what I said, if something is operating at 30% versus 100% or 90%, something that has mostly capital costs, it's going to be 3 times cheaper. Okay, questions?
Iceland was mostly geothermal or hydro?
I think it's, Iceland is mostly geothermal.
And it's
Yeah, I mean, you know, got a lot of engineers and people who spend a lot.